It's more about giving us a break. All right. Okay, good. So yesterday we talked about noble liquids. That's what we ended up on. So I wrote down here again various detection concepts for low mass dark matter. And we did some detailed dark matter electron scattering, just sort of the kinematics to get a feel for it. Hopefully that's useful. That's sort of applicable for lots of different materials as well. So some of the intuition that was developed is useful for other things as well. So we'll do the rest in a little bit less detail. So I ended up on this. I mentioned that the best limit, I didn't show you the limits, but I mentioned the best limits right now on sub-GeV dark matter electron scattering actually comes from noble liquid targets, at least down to 5 MeV, okay, by quite a bit. And there's lots of other ideas out there though. And I also told you about some of the problems that these noble liquid, the xenon TPCs or argon TPCs are facing. And there's people trying to deal with those backgrounds that they have, and we'll see how successful they are. So there's other very promising things which I want to discuss today. So next up is semiconductors. All right. So here, the classical examples are silicon and germanium, although all the results so far that exist, as we'll see, are just silicon, and also the proposed experiments are mostly silicon in terms of dark matter electron scattering. There's some germanium as well, but silicon is is the more important material at this stage. So this is very promising to probe lower masses because the band gap, so semiconductors have a little band gap, and let me just draw sort of a simple energy diagram. So instead of having quite a large ionization energy that you need, about 10 eV, so 12 eV for xenon, we actually have here, so what I'm going to draw is a band structure plot. So if you remember some basic solid state physics, so a semiconductor is something that has valence bands, and then there's a little bit of a gap, and then there's a conduction band. And all the valence bands are filled, and if you promote an electron from the valence band to the conduction band, you can conduct it, okay? And just to sort of give you a very schematic picture for silicon, for example, very schematic. So here's some band structure plot, which I'm going to try and pretend to draw here a little bit. Okay, some random bands, and let me draw it like this. Okay, very schematic. And here you've got other bands. Okay, just drawing randomly stuff, and there's bands up here as well. And the idea is that this is the valence band. So these are the electrons that are most loosely bound in the crystal. So you've got a crystal. The electron is moving sort of in a potential that's is feeling the lattice. The various nuclei. And this is a filled valence band where the electrons are sitting. Then there's a little bit of a gap. And then you've got a conduction band going up. Okay. And the gap in silicon is about 1.2 eV. And for germanium, it's even less. It's 0.67 eV. Okay. And the idea is that dark matter can come in, hit an electron here, scatter off the electron, and promote this electron across the band gap up, somewhere high up. And in particular, the lowest energy you can promote the electron to, so if I just take an electron, for example, on the top here, then it can promote it to 1.2 eV above. And what you leave behind is a little hole. So you have a hole left behind, and the electron that you create. And of course, what you can also do is promote the electron higher up in the conduction band. Now, the nice thing here is that silicon actually has an indirect gap. It means that the highest valence state is not directly not at the same momentum point where the lowest conduction band state is. And in fact, what we know, right, is that the typical momentum transfer is about a few keV. and that means the typical energy transfer is a few eV. And the nice thing about an indirect gap is that you need to transfer momentum in order to also transfer some energy. So the dark matter needs to transfer some momentum to the electron, and that also gives it some energy. So quite naturally, you actually have an indirect gap transition that you want to take advantage of. So that's the lowest possibility, 1.2 eV, or 0.67 for germanium, and that allows you to probe down to 500 keV dark matter. Okay. So let me just write E gap for silicon, 1.2 eV, and for germanium, 0.67. Okay, good. So now what the dark matter does, it creates this electron hole pair. If the electron goes quite high up in the conduction band, what happens is that this electron will fall back down to the bottom of the conduction band, and then that's going to actually lose energy. And what happens with that energy is going to create additional electron hole pairs. And on average, in silicon, for each 3.8 eV of energy that you give the initial electron, you get an additional electron hole pair. Okay, so what you end up with, if, for example, you give energy to the electron of 1.2 eV plus 3.8, you're actually going to get 2 electron hole pairs. Okay? And if you give it 2 times 3.8 plus the band gap, you're going to get 3 electron hole pairs. So you can get multiple electron hole pairs, and there's some spectrum that you can calculate. Okay? So let's say dark matter interaction creates multiple, or let me just say creates electron hole pair. And for each 3.8 eV of energy in silicon, it's a little bit less in germanium, you get an additional electron hole pair. So at the end, you've got multiple ones. Okay? And also some of the energy, of course, if you excited to high up, the electron high up to the conduction band, what can happen to that energy as it falls down, you see the band gap is only 1.2 eV. So it requires 3.8 eV of energy actually to get an additional electron hole pair. That means some energy is actually going into phonons, something else. Okay, so the way you can look for this kind of system, this kind of signal, is that you can look, of course, for the charge, the electron hole pairs, or you can look for phonons that get generated as well. Okay. All right. So now. Again, the form factor will drop very sharply as a function of momentum, so the spectrum actually is very sharply peaked at low energies. And just to show you roughly what it looks like, so the spectrum folds sharply versus as a function of energy. And schematically, if this is my deposited energy, I'll get something like this, where at about 40 eV or so, compared to a few eV, what we get is that just ignore what the precise units are, but basically this is about 7 orders of magnitude difference in terms of what the spectrum will look like for like a 10 MeV dark matter particle interacting with some heavy mediator. The difference between the rate at 5 eV and the rate at 40 eV is about 7 orders of magnitude. Okay, so it's a huge rate. So, for example, m chi equal to 10 MeV. The rate difference between here and here is 10 to the 7. And what this means is that if you have a detector that's able to sense electron deposition energies of about like 40 eV or so, you're going to get some number of electron hole pairs generated, some number of events. But if you're able to lower this threshold to probe your much lower energies, you get a huge gain. Okay, so it's like a big change, 7 orders of magnitude in this particular example for this mass. So the rates that you see, rates in detector, or rates detect, let me just say, the number of events detected increase sharply, very, very sharply, for lower thresholds. Okay, any questions on this so far? Yeah.
Each 3.8 electron volt of energy corresponds to another dark matter mass?
Say again, sir.
Each 3.8 electron volt of energy additional corresponds to another dark matter mass?
No.
Or
so it's the dark matter hits the electron and gives it energy. And there's a spectrum of what energy it gives. And what I'm saying is that if it gives a 1.2 eV of energy, you get 1 electron, one electron hole pair. If it gives it 1.2 plus 3.8, so 5 eV of energy, you get 2 electron hole pairs.
So why it has to be the same dark matter mass and not different? Because you said before that, right? In this scheme,
So
we are looking at a specific dark matter mass. Right?
So we're looking for, so we can calculate this for different dark matter masses. So for 10 MeV, I get this spectrum. So what I can do is I can bin it in 3.8 eV bins, okay? And that's the number of electron hole pairs I see, 1, 2, 3, 4, 5, 6. Now I've got a different dark matter mass, like 100 MeV, so it's going to look a little bit different, right? So, well, just very schematic drawing, something like this, okay? It's going to give a different spectrum.
And you can do it for any?
Of course, you can do it for any dark matter mass, yeah. And then if you actually see a signal, right, and you believe it's dark matter, then you can say, okay, what does this correspond to? Is it 10 MeV, 100 MeV? What's the mediator? This spectrum also depends on how is it interacting. If it's a light mediator, the cross-section goes as 1 over q to the 4th, so then it's peaked at lower momenta, lower energy. If it's a heavy mediator, it's going to peak slightly at higher energy. Is that okay? Good. Thanks. Other questions, please.
So this 3.8 is part of that, like a phenomenological modeling that estimates how many electrons, right?
Yeah.
Do you expect the number for all semiconductors to be roughly around a few eV?
It's roughly a few times the band gap. So yes, right. So germanium is a little bit less because the band gap is smaller. That needs to be measured to be sure, right? That has not been measured. People have made models for this. It's not really it's also on average, right? So sometimes something that gives you 5 eV of additional energy is not going to give you an electron hole pair, right? So there's some Poisson process going on as well. Other questions? Yeah.
Sorry, this is sort of like the same question as yesterday, but why wasn't this measured? This also seems like something.
This can be measured now.
Oh, okay.
Yeah. But the reason it wasn't measured yet is because we didn't have the detectors until recently, right?
You had it before?
For 2 years. Yeah. But I mean,
Oh, recently too.
yeah. You're very young, so recently means different for you than for me. Okay. But yeah, no, this is something that that can be measured. All right. So this was the situation, right? Basically, before 2017, you couldn't be sensitive to electrons below about 40 eV of energy deposition, and now we have several devices that are able to sensitive to this. So there's a big change over the last few years where now you're able to sense even single electron hole pairs, and there's several devices that can do this. And I want to very quickly talk about these. Okay. So I think this is sort of important because it's a very recent thing, and it's worth appreciating it. So before 2017, best detectors they were limited by noise, so they're not sensitive to less than about 10 electrons, right? So 40 EV, very roughly divide by 3.8, right? That's about 10 electrons. So we're not sensitive to less than 10 electron in silicon, okay? Now we have several devices in the last 2 years okay, and I want to discuss them very briefly. So what I'm going to do now is I'm going to discuss the devices that can measure electrons very briefly, and I also want to then sort of, before I go to the other ideas, I want to tell you about very briefly about other devices that can also measure single photons and phonons. Okay, so I want to quickly give you an overview of the kind of devices that exist now and what the near future is for these. Okay, so but in particular for single electrons, there is skipper CCDs. Then there's transition net sensors, and there are things called depth FETs. So these can all measure single electrons, and they've been shown to be able to do that. They can resolve single electrons, single electron pairs. And this is used by, or demonstrated first by Sensei. This is by superseding mass. And this is a collaboration called Dene. Okay, so this is for measuring electrons. Now, TES is actually multi-purpose, so they can also measure phonons, very small energy depositions in terms of heat, and also photons potentially. And then there's also devices that can measure, other devices that can measure photons. So there is superconducting nanowire single photon detectors, SNSPDs, which I'll very briefly talk about. And I will also mention, let me just say gamma or phonons. Well, let me just give it gamma again. And there's also MKIDs, microwave kinetic inductance detectors. So very briefly mentioned, go through these things, okay, and tell you how they work.
So do all
Questions?
these devices require heavy shielding, like 7 ton, or like the cosmic ray spectrum is different?
No, so these are there's several questions you have to ask. So these are devices that can sense the small energy depositions. Now you have to ask what other crap can cause a signal, and for that you need to shield, you need to have a pure material and all that stuff. So I'll talk about backgrounds a little bit after this. Yeah, but this is the first question: is can you sense it? Right. First theory question is, what kind of signal can you potentially generate that you might be able to see, right? And does the kinematics work out, etc. Right. So for elastic nuclear recalls, they don't. So then there's all these other ideas that we'll talk about, where you're able to deposit enough energy. Second question is, does a device exist that allows you to measure this tiny energy deposition? And the third one, can you control backgrounds? Can you actually build an experiment? Can you make it a gram scale or kilogram scale experiment without backgrounds, etc. So those are all things that need to be satisfied in order to have a meaningful dark matter experiment. Okay. And many ways, this field has been theory driven, right? Where theorists have come up with a lot of ideas, and to actually do the real thing, that takes a lot of effort. So instrumentalists and experimentalists are sort of catching up to all the possible ideas that are there to see if one can actually measure these things. Okay, but there's been huge breakthroughs in the devices. So let me very quickly talk about these devices. Okay, so skipper CCDs, they were developed in 2017. It's actually an old idea back to the 90s, I believe, but they were only shown to work properly recently. So if you think about a CCD, so a charge coupled device, so basically it's a thing that consists of order 1 million pixels, so it's a thin little thing where there's pixels, some silicon device, where the scale of this will be potentially a few centimeters, the scale of that will be a few centimeters, and the thickness of this will be a few hundred micrometer. Okay. So thickness and we can just say order centimeter. And CCDs are used for many years already, right? Many decades already, many years already to measure photons. And what they do is, if a photon is incident on a CCD, it creates electron hole pairs, and then you read out that charge. And that's what CCDs do, and they are able to take beautiful images for, astronomers use these things to take beautiful images of galaxies, for example, and they have many applications. And the way these things work, so there's about a million pixels, and you create some charge. And this could be dark matter. In our case, of course, we care about dark matter creating some charge in some pixel, or it could be a photon creating charge principle, right, or some other interaction. And then what you have is you've got these, looking from the top now, we create some charge, let's say, in this pixel here, And what happens is that in the corners, in each of these corners, so you can put multiple things on there, but you can imagine that in each of these corners, actually, for simplicity, let's just take one corner. In one of these corners, there's a place to read it out. There's some readout stage. And what happens is that you shift the charge pixel by pixel until it gets to this readout stage. And what's at this readout stage is that you can think of it like a little capacitor. So you move some charge to the capacitor, it creates a voltage, and you measure the voltage. So there's some voltage readout that you have here. Okay. And whenever there's some charge that's moved to it, you measure a voltage, and that's your measurement. And CCDs, so you can do fancy things, and the CCDs, ordinary CCDs, they have a readout noise of about 2 electrons. So you're uncertain every time you make a measurement, which is a voltage measurement, but then you convert it, of course, knowing the capacitance, you convert it to a charge. You're uncertain each time you make a measurement of about 2 electrons, 2 to 3 electrons, what measurement you actually made, of how many electrons are in that pixel. And this then means if you make 1,000,000 measurements, because you have 1,000,000 pixels, there's, of course, a huge distribution, just a Gaussian distribution that you get. And if you want to be sensitive to single electron pairs, you can't do that with a 2-electron readout noise, because you're sometimes going to measure 5 electrons, sometimes -3, right? There's always uncertainty. There's a Gaussian uncertainty. So this is not a great device if you want to sense single electrons, but that was a state of the art a few years ago, so that's why the threshold is about 10 electrons, so 5 sigma away. 5 times 2 electrons is 5 sigma. So that's why you're able to sense things that are above the noise, only if it's about 40 eV energy to position. But the skipper, what it allows you to do is, what it does is that the readout stage is modified, everything else is the same, and you're able to move the charge packet that you have back and forth 100 times, 500 times, 1,000 times, and repeat the same measurement of the same charge packet. So the charge does not get destroyed, it just gets moved back and forth. And you repeat the same measurement 100 times, 1,000 times, whatever you want. Okay. And that then lowers the noise. So by repeated measurements, repeated measurements, it lowers the noise, and the noise will be 2 electrons divided by root n, where n is the number of measurements, number of samples you've taken. And that then this then allows you, if you have a few hundred measurements, that allows you to lower the noise to well below an electron, and now you're able to precisely measure the amount of charge in each electron, in each pixel. Okay, and that allows you to get to single electron sensitivity. And that was demonstrated in 2017, and that then allows you to make a very sensitive detector. Okay. Can detect so the noise was demonstrated to be as low as about 0.07 electrons. Okay. So now you've got a great dark matter detector. Okay. And now, so there's several experiments that are going to take advantage of the skipper CCD. So yes, please.
So does it only measure that there is an electron, or does it also measure
So the momentum, the position. So once the electron gets a kick and it gets promoted to the conduction band, it creates a few electron hole pairs in a pixel, and that then sits there. So there's some voltages that make it sit there, and then you move that whole charge pixel by pixel to the readout stage. But the initial interaction is completely lost, right? There's no momentum measurement. It just measures what charge is in that pixel. Yeah.
How do you not lose your electrons when you measure once? Because I expect like they create a current, that's it, you lost your electrons. Or they
So-
destroy voltage, you lost your electrons.
Well, so you have to, you can show that experimentally that you don't lose them, but the answer is that there's a very good efficiency to move the charge from pixel to pixel, so that you just don't lose them. Okay, that's a very, very efficient process, moving in pixel to pixel without losing anything.
Yeah, that's
Yeah.
okay. I'm okay with moving them from pixel to pixel. I'm not sure though how when you measure, in the last pixel, how do you not lose them when you measure?
Because it's just, I mean, think of it like a little capacitor that sits there, right? You move the charge there, you make a voltage measurement, you just move the charge away again. I mean,
with the same mechanism.
yeah, I mean, there's various, there's metallic surfaces sitting on this which create the potential, and so you just change the potential and you just move the charge. And you do this very quickly. Okay. Okay, so this was demonstrated by Sensei, which stands for sub-electron noise, skipper CCD experimental instrument. So sub-electron noise because the noise is, of course, less than an electron now. Skipper CCD, that's what the thing is called. Okay. And now, so what was done already was that they were, so this is all very recent. So then a prototype detector was used to set the first limits. On dark matter down to 500 keV masses. Oops. Okay, so about EV band gap roughly is 500 keV masses. Actually, let me put this here. So in 2018 and 19. And now the goal is to put a lot of them together. This prototype was a tiny little CCD. It was just 0.2 gram big. Just to show you a rough size of how big these detectors are, they can do new science. I think this is something that's generic for this whole field. If you have a new small device that can do new physics, this is the size roughly. Okay, that's the dimension. If you can see this little cardboard cutout. It's this big, they can do new science. Okay, and it's the same with other detectors, the TESs that we're talking about. These are tiny little devices that can already do new physics, just because you're accessing a new range and parameter in energies that you're sensitive to. You could put them in cameras, but it's too slow. So the problem with a skipper is that you multiple sample the same charge, so it's very slow, the readout, compared to an ordinary CCD. Yeah. So for a 1 million pixel CCD, if you want to have a good charge measurement, it takes an hour to read out. So you don't want to wait for your iPhone, right? You want to take a picture, and you want to look at it.
Right, but maybe astronomers, this is important. Like if they need low noise.
So yeah, so there are people developing applications for astronomy. It's not as obvious that it's going to be super revolutionary for that, but people are thinking about it for sure. Yeah, because it's slow. Yeah, and it's not always clear that you need the super low readout noise for many applications, but for some things you do. But yeah, if you have ideas, I think people will welcome them.
I mean, how many times are they repeating the measurement?
It varies. So how good you want your noise. So it depends how good your single sample noise is, how good this initial noise is, but 500 times, 800 times.
Because if you just want to reduce your noise by 2, you only need to do 4 times, right?
Right.
So
yeah. So that if that's something that does something for some application, that's good. Yeah. Okay. So now several experiments are doing this. So so by 20. So Sensei goals, so let me just, Sensei goals to have a 100 gram detector with these skipper CCDs running by end of 2020. Not 2200, 2020. 0 needs to be in the middle. It's by end of 2020. There's an experiment called DAMIC M. M stands for Modern. So Sensei will be at Snow Lab. DAMIC M Modern, there's an experiment that's being planned to be put at Modern. This is going to be a kilogram of skippers by, let's say, 2023. These are both funded experiments. And then there's a third effort that was funded for R&D purposes, which is called Oscura, which has a goal of doing 10 kilograms of these skipper CCDs by, I don't know, making stuff up, but maybe 2025. Okay, and the R&D for this is funded, not the experiment itself. Now, I'll talk a little bit about backgrounds in a few minutes, But this gets progressively harder. Okay, this gets much harder, and this is a super ambitious experiment. Okay, there's a lot of things that you need to take care of, and I'll talk about backgrounds a little bit. And this is true for anything. So any device that you want to think about, here you really need to worry about the Compton background. You need to worry about it the whole time. But the more mass you have, the more if you want to be background free, you need to work really hard to have very pure materials, very good material handling. Yeah.
These are all silicon?
All silicon skipper CCDs. Yeah.
In principle, you could. Is there any reason not to do the skipper CCD out of a different, let's say, germanium or any other material?
Yeah. So people are thinking about that, germanium. Yeah. So it's just that CCD technology exists. It's been developed for ages for silicon. Germanium, people are looking into that. The bandgap is a bit lower. I don't know all the challenges exactly to transition this. If it's just sort of a historical thing, there might be other challenges. Yeah, I'm not the right person to ask. Yeah.
So what would this detector say the interaction of the dark matter with electrons?
Yeah. You can also look for dark matter nuclear interactions where the nucleus gets a kick and creates some charge, right? So just do the elastic nuclear recoil. And you can also do something called the Migdal effect, where you also create charge, which I'll talk about later today. So there's other things that you can actually probe. You can also probe dark matter nuclear interactions with these detectors. Same thing with TESs. Anything that measures charge, you can actually also probe dark matter nuclear interactions from the Migdal effect. So I'll mention that later. That's actually an important thing. Mm-hmm.
Just in terms of the overlap of the experimentalists or the instrumentation people who are making these experiments, these proposals, like who's on Ascora? This is my first time hearing about it.
So these are distinct collaborations at the moment.
Okay.
But I mean, people are in close contact. Oscura combines both people. So right now it's a very small, it's just got funding recently by the Department of Energy in the US. And it has to be a huge effort eventually. It's going to combine everyone in the community basically to do this because it's a big effort.
So how exactly is this experiment done? I know like camera terms like exposure, like how well would you expose this for?
Yeah, so typically the time scale that's useful is a year. Right, so you think about 100 gram a year exposure eventually, kilogram a year, 10 kilogram a year. But if you have, so if you have this experiment, right, you can see these as prototypes for this, right, if you like, because you're going to learn, right? But these are huge experiments by itself, of course. But this, if you have this running, it's a multi-million-dollar experiment, more like order 10 million, probably more, with all the people involved, much more. Then you want to run this for a few years. But that's the time scale, right? Sort of grad student lifetime. Yeah.
Making larger is just about making surface area.
No, so you can't make them too large because otherwise it takes you a day to read out the CCD. One problem that these devices have still at the moment, I mean, these are still new, so they're being understood, so there's lots of things people are learning about them. But one issue that we know about, which we don't know how severe it is the dark counts. So these CCDs sit at a temperature of about 100 Kelvin. Who asked the question? Sorry. Oh, yeah, sorry. I'm trying to figure out where to look. Thanks. So these CCDs sit at about 100 Kelvin, maybe 130 Kelvin, which means that you've got some temperature there. And the reason they need to be that warm, as opposed to being like 1 Kelvin or so, is because if you make it too cold, then you can't move the charge. So these things become non-conducting, these things that create the pixels essentially, and you can't move the charge from pixel to pixel. So they need to be reasonably warm compared to cryogenic temperatures, right? But that means that you can actually also just promote from thermal fluctuations electrons from the valence band to the conduction band. So you're going to get single electrons actually in the CCD. And the hope though is that this thermal fluctuations, that rate is low enough that you won't get 2 electrons being promoted while you read the thing out in a single pixel, so that you have a 2 electron threshold, for example. But having a single electron threshold that's background free is impossible. Hope is that maybe you can have a 2 electron threshold. So now if you make this huge, right, this CCD, it takes you longer to read out, so the dark current is going to be worse. Okay, so you don't want to make them that big. So what you do is you just make more of them, which creates problems, challenges with electronics. You have to read out many, many CCDs, etc.
So while you read out the CCDs, it takes time, and during this time, there's a chance, another electron gets excited, even by dark matter.
Yeah.
So does that put a constraint on the sensitivity? Because if you have dark matter constantly creating excitations.
Yeah, so that'll be very
That's the
exciting,
problem.
right? If it
Yeah,
comes
I
to
know,
great
it would be
excitations.
exciting,
But
you
yes,
would not be able to tell that from the background.
right. So it's right. When you read out an image, you don't quite know when the event happened, right? But that doesn't matter because what you do is you look at the spectrum. At the end, you just have the number of events versus number of electron hole pairs that you create. You don't really care if it created it here or here during the readout while you're reading it out. That's not important.
Right, but if we see both here and here, then we can tell whether it's a background or it's a...
From that, you won't be able to tell if it's a background. So
Right.
for the background, really the challenge will be to look at the spectrum and to make it shielded really well and see if it's Poisson distributed, that maybe it's, like if these thermal fluctuations, it'll be Poisson distributed in terms of the 1, 2, 3 electron peaks. Yeah, but the timing information is lost, essentially.
So even if it takes you an hour to read it out 1,000 times, you don't have a dead time of an hour, right?
No, you're still exposing, yeah. And so there's different ways of running this, and the question is what's optimal. That's still up. It's still not clear. But even as you're reading it out, you're still exposing, right? And you can read it out continuously if you wanted to, right? That's one mode of running.
I think I'm still a little confused about how the skipper actually improves the noise. So you move electrons onto basically your capacitor that you're reading out the potential on, right? And then you move them off, and then you move them back on, and you repeat the measurement, right? So if it's very, very efficient to move these electrons around, why is it less efficient why is that last step to the capacitor actually the source of noise? I mean,
You make a measurement of how much charge you have, right? So you read a voltage out, and the best electronics that people have been able to do is about a 2 to 3 electron uncertainty on one measurement. But if you make 1,000 measurements, right, you get to take the average.
But if I move them onto the capacitor successfully, and then I read them out, then why can't I just immediately repeat the same? Why do I have to move the electrons back off and back on?
Because you want to reset it to 0, and then you.
So there's some fluctuation.
Yeah. So you move it away. So yeah. So we can talk more about it afterwards. But okay, let me move on now a little bit. Okay. Good. All right. Yeah.
The first bound of 500 kV, the total prototype, what was the size of this prototype in comparison to these?
So the new ones will be this big.
That's the one.
The new ones, yeah. Those are not the prototype. Yeah. So there'll be 50 of these. Okay. And the prototype was one of these, and that's like 0.2 gram or something.
And you said building a larger detector is much harder. So what's the difference between just exposing 1 kilogram and 1 kilogram detector for here, and instead of exposing 10 100 grams of detectors for the same amount?
Backgrounds, and let me talk about that a bit later. Okay, so the Compton background is going to be important. I'll talk about this a little bit later. Okay, so hold your question. If I don't answer it to your satisfaction, remind me again when we talk about it. Okay. Good. So let's move on to the second one, TESs, and very quickly tell you about how these work. I guess could have kept that. Okay. Anyway. All right. So transition net sensors. So TESs are great devices. They have multiple applications in terms of the dark matter field. So with them, you can detect electrons, photons, and phonons. Okay. So these are operating at cryogenic temperatures, so very, very cold, 100 millikelvin or so. And the idea basically is that what you have is a thin superconducting film that is voltage biased, and it's the voltage is chosen in such a way that the device sits exactly at the transition between superconducting and non-conducting, so that if you give it a little bit of temperature, it changes from superconducting to non-conducting, and that changes the resistance by a huge amount. So basically, if you draw a little diagram, let me just write this. So superconducting, thin film, that is voltage biased. So its resistance is in the transition between superconducting and normal. So on a little plot, as a function of temperature, if you look at the resistance, this thing sits at a transition where you have something like this, and you put it here, and if you add a little bit of temperature from a phonon or from a photon, for example, there's a huge change in the resistance. Okay. So small change in T, big signal. The devices are small, so these devices are 25 micrometer by 25 micrometer by 400 nanometers big. So the devices have mass by itself of like 500 femtogram, so very small devices. So you can't use the device itself to do a meaningful dark matter experiment, right? They would be very sensitive, but it's just such a low mass that you can't really probe any meaningful parameter space. So 500 femtogram. But what you then want to do is you want to take this device and couple it to a much larger volume, which is your target. So your target, unlike the skipper CCD, where the sensor in some ways is also the target, for the TES, you want to have a target, and then you want to attach the TES device to that. Okay. So there's a question about what you can detect, sense above noise, and I'll tell you some numbers soon. So right now, they've made TS devices with a sensitivity of like 200 millieV. Okay, but these are small devices, 200 millieV resolution, energy resolution. So if you're able to sense above noise, roughly, to like 200 millieV. I don't quite know if that answers your question, because I don't know if that's the same as what will displace it. I don't know. My limitations as a theorist are showing again. Okay. So right. Okay. So you can attach these devices to a larger volume, to a target, and then detect photons, for example, or phonons coming or created in that target. Right, so the idea is that you've got some volume, and then you just attach your TES devices to this. And that's your big target. And this allows you to, for example, have a scintillating target, which I'll very briefly talk about in a few minutes, where you have some scintillator that will create photons from some dark matter electron scattering, for example, and that photon is going to get to your TES device. Okay, or it allows you to look for dark matter nuclear scattering, which I'll talk about later this afternoon, where you create some phonons, where the phonons will bounce around a few times. They can be quite long-lived. If it's some athermal phonon, it bounces around quite a while and eventually makes it to your TES, and you can sense it. You can also imagine using a superconducting target, which I'll again mention very briefly a bit later, and attach the TES to that to look for very low energy depositions for dark matter electron scattering. And also you can use them to sense electrons, and that's what they were used for recently. That was the other breakthrough that I was talking about in 2017, where people actually, from a super CMS collaboration, managed to sense single electron pairs with these devices. And what they did was the following. For electrons, you can imagine taking, schematically, you have your TES device. I don't know why I'm drawing 2, but let me just draw 2, whatever. And you've got your silicon target, so this is silicon here. You attach your TES device on top and bottom, for example, and then you create an electron hole pair, and you apply an electric field across this. And what happens is that this electron gets pulled and the hole gets pulled, okay? And as it gets pulled, what happens is that the electron rattles around in the lattice and creates phonons. So you create phonons. So voltage or electric field pulls electrons and creates phonons. They're called negative loop phonons, but it doesn't matter the name. Well, let me write it anyway. So it creates negative loop phonons. And these are then detected by the TES, measured by TES. Okay. And as long as your resolution of the TES, the energy is good enough, you can detect single electron hole pairs, which means that if you create 2 electron hole pairs in your device from some dark matter interaction in the silicon, you have 2 electrons moving up and 2 holes moving, 2 electrons moving up, 2 holes moving down, and you create twice the number of phonons. And if it's 3 electrons, 3 times. And they were able to resolve that in a very nice experiment. How precise are temperature stabilization techniques? You mean how precisely can you keep the temperature there? I'm not the right person to answer that with with quantitative precision. I think it's pretty good. Yeah. So maybe someone else knows here, but I think it's pretty good. Yeah, the worry is more about vibrations and electromagnetic interference that can mess things up, and that's a bigger worry. I don't think that keeping a particular temperature, that's not the challenge, I think. Okay.
Yeah, thermally it's very quiet.
Yeah. Okay. So then there was some, demonstrated, so there was an experiment called CDMS HV, where this stands for high voltage. And they demonstrated noise that was well below 1 electron as well. Okay. So again, you can resolve single electron hole pairs. And that again allows you to do a very sensitive dark matter search. And the challenge that they have is also they also have some kind of dark counts, because you create an electric field, which means that you have electrodes sitting around that create this electric field, and those can spit off electrons. So there's leakage currents, so they'll just emit electrons randomly. So you will get single electrons that will just get randomly generated that you sense, and that's a background. Okay, and of course there's work going on to try and lower that. So this was in 2017. And first dark matter results using a tiny device also in 2018, and more work is going on. So these things are being improved and more data is being taken. And I haven't looked at the archive in the last week, so maybe they have even a result out. I don't know. Okay. Good. All right, and then also, right, so these devices, as I said, are multi-purpose, so you can also sense, this is one way to measure electrons, but also, as I was mentioning, right, even if you don't apply an electric field, and if your TS has a very, very good sensitivity, what you can do is, if the electron gets promoted to the conduction band sufficiently high, and as it rattles down again, it'll create some phonons, right? So you can actually measure electrons also by just looking for the phonon signal itself without applying an electric field. But you need to have a sensitive TES to do that. And then for photons, right, you can look for photons and also phonons in principle. And what you want to do is you want to lower the noise of these devices sufficiently, make it sufficiently small that you can measure very, very, very tiny energy depositions. And the ultimate goal, right, sort of the dream goal, will be to detect energy depositions of as little as a milli-eV, right? And then these devices would be amazing. Okay, so right now we're not quite there yet, but that's sort of the goal. So the state of the art right now is that, as far as I know, so there's work by Matt Pyle at Berkeley and collaborators, where what they've managed to do is they've got a device. Let me actually put this up here. So there's a 3-inch device. So let's use proper units. 45.6 centimeter squared area device. That's attached to silicon, which has a 16 eV threshold. Okay. So with that, you can look for dark matter nuclear interactions in silicon that create 16 eV of phonon energy. That's going to get you to sense about, so you can get a nuclear recoil limit, or sensitivity, I should say. Maybe there's a signal. Down to 500 MeV. You can also look for electrons, but it's still pretty high threshold. Okay, so you're not really going to compete because of the sharply falling spectrum for dark matter electron scattering. You can also have smaller devices which have a sensitivity that's better than this. So within a year, you can imagine, within very roughly order a year, could or should have devices sensitive to 1 electron, 1 EV, I should say, sorry, 1 EV. With that, you can lower the nuclear recoil threshold. You can send single electrons without even applying a voltage. Right, applying the electric field, that creates a lot of energy, right? So you don't need to have a super low threshold in order to sense that. That's why they apply an electric field to create a larger amount of phonon energy that they can then detect. But once you've lowered the TS sensitivity down to an EV, you don't even need to apply an electric field. And then there's work going on to lower this even more. And the hope is that once you get it, so this also allows you to sense photons of 1 EV, okay, which is great, which is going to be relevant in a few seconds when I talk about scintillators. And so detect electrons and gammas and phonons of 1 EV. Okay, that's going to be amazing. And then there's work going on to lower it. The goal will be to eventually get down to 1 to 10 millieV. And of course, it gets harder and harder the lower we go. Okay. So I think this is pretty exciting. There's lots of things going on. Okay. And the challenge for these things is environmental noise, electromagnetic interference. Right. These are all electric devices. They couple to some electronic system. There's noise. You have to isolate things. You have to filter things. It's challenging. Yeah.
Just wondering, how can you fit your mass hypothesis on such low signal? As you show the spectra for different masses, and if you have such a low deposition of energy.
Well, this just means that you're able to sense down to that level, right? Of course, you can sense higher energies as well. No. So the idea would be that this is the energy deposition. So now that means, right, so we know that 1 EV of energy is the kinetic energy of an MeV dark matter particle, roughly. Okay, so that you're able to sense MeV dark matter.
Sorry, but I probably missed something very basic. When the threshold is 16 EV, you map that to the nuclear recoil.
Yeah, so this is just in silicon. So roughly, I think it's 500 MeV. Maybe I got the number wrong. But this is basically the energy deposition of a nuclear recoil, which is, remember, it's Q squared over 2mn. And Q is mu chi n times V. And just putting the numbers in. So that's basically the first lecture that what we did. So it's roughly that allows you to get down to 500 MeV.
Right, but this is not, is this based on nuclear recoil? I thought this is like...
This is like, these devices can do anything. Right? These can do various things, right? So if you just look for phonon heat deposition and from nuclear recoils, you can get that. You can look for electron recoils down to 16 eV, but remember that the spectrum falls very sharply, so that's actually not that great an experiment yet for electron recoils. This would be a great thing, right? By applying a voltage, they have these huge backgrounds, dark currents. So, but that allows you to put in energy to the electrons that increases the phonon energies that they're able to sense it. But without an electric field, you want to be even more sensitive because you're not putting energy into the electrons.
Okay, so essentially the TES is the device that senses the change in the voltage, and anything that creates phonons can be solved.
Yeah, anything that's in phonons, yeah. So the way you detect the electrons that you, right, in this case, you apply an electric field that creates the phonon. So they don't detect the electrons itself, they detect the phonons that get created. Just like a xenon TBC, you create an electron, but what you're actually detecting is you're using PMTs to detect the photons that get created when the electron bounces around.
So the high voltage, the CDMS high voltage device doesn't actually have a low threshold TES. They just have sub.
Yeah, I mean, it's a great TES, right? It's a great
Yeah,
TES.
yeah,
But it doesn't, you need to put the electric field in to get the single electron hole sensitivity. Yeah. Mhm. Okay, good. Good. I said the challenges, I'm not going to write them down. Okay, so environmental noise and electromagnetic interference. Okay, so there's other devices. So I'll just mention them. I will say much less about them. So there's DEPFETs that I said before. So DEPFETs stand for depleted p-channel field effect transistors. And what they do is actually they work very similar to skipper CCDs. You can think of them as skipper CCDs, just bigger with fatter pixels. And they also have repeated measurements of the charge. And that's a device that was also recently demonstrated that they can measure single electron pairs, but they also have dark counts. So that's, I think, in terms of the R&D efforts, they're behind the skipper CCD effort, but they're devices that are being looked at. Okay. Silicon. Yeah. Okay. And there's an effort by Danae, an experimenter, to use them. So R&D efforts ongoing, but have demonstrated single electron hole pair sensitivity. Okay, and then there's MKIDs, which are microwave kinetic inductance detectors. So those, you can think of them as a little LC circuit. So there's some inductance and some capacitance, and there's some resonator. So if you drive that circuit, if you remember some basic electronics from undergrad or something, you can basically, there's a sort of certain resonance frequency which depends on the inductance and the capacitance. And if you change the heat of that system, so if you absorb a photon, for example, that'll change the inductance a little bit, and that's going to change the resonance frequency a lot. So you're going to basically go off the resonance. So they're sitting on the resonance, and then they get off it by a little bit of heat deposition, and they're also able to sense, like TESs, very, very tiny energy depositions. And at the end of the day, what's better to use for dark matter experiments like TESs or MKIDs, I don't know the ultimate thing, what's going to be better at the end. TESs, I think, for dark matter applications are much more, have been thought more about, I think. I think that's fair to say. Okay. And then finally, S and SPDs, so superconducting nanowire single photon detectors. So the name says what they do, right? They detect single photons. So they are basically a thin wire of superconducting material, so 5 nanometers thin, 100 nanometers narrow, and then the length of about a few hundred micrometers. And again, they're cooled to be below the superconducting transition, and they are basically, there's a current flowing through them, and so it's superconducting, and as soon as there's some heat deposition from some photon that gets absorbed, it changes the resistance, and you get a big effect, like you get a big signal. You can sort of get a voltage pulse to your electronic system. So they're able to sense single photons. Okay. So maybe what is useful, rather than discussing these things in more detail, which I think it's more important to discuss some other things, but I can just make a little table to summarize these things here. So summary of devices that exist. Right, so this field of sub-GeV dark matter detection wouldn't exist without theorists coming up with ideas. It wouldn't exist without experimentalists developing amazing devices and instrumentalists. So there's a lot of progress that's needed to of course, to get some real experiment done. But the devices are crucial, obviously. And here's the device. And what does it detect? So we talked about the two-phase TPC. So it detects electrons very well. It has its challenges with in xenon and argon with backgrounds. We have silicon skipper, CCDs, which can detect electrons in terms of the dark matter. What we care about for dark matter. It, of course, can also detect photons, but people haven't really thought about using it as a photon detector, like from attaching it to some scintillating material. But electrons is what it's used for. TESs, which have electrons, photons, and phonons. And then there's the MKIDs, which are phonons and gamma. And I guess you can also do some CDMS high voltage to do electrons as well in principle, I think. And then there's the DEPFETs, which are electrons, and SNSPDs, which are photons. Okay. And then for the SNSPD, I should say, right, so you need, and collaborators have actually got a limit using SNSPD on dark matter electron scattering and superconducting material. So I'll talk about superconductors very briefly in a bit, but there's also been a limit using these devices are also not very big, they're not very massive, but you can actually also already set a limit on these using a single device, right? It was one device I use, yeah. Okay. So a lot of cool things going on. Okay. Good. Questions? While I erase. Okay. Okay. So backgrounds, I'm going to briefly talk about those. So backgrounds, I mentioned some of them already. So some of them are just sort of, let me call them detector specific. Right, dark counts for the skipper CCDs or for the CDMS high voltage, or for the xenon, you know, the TPCs, argon TPCs, there's detector-specific backgrounds. These need to be overcome, right? And there's hope that one can do that. Then the thing that one typically thinks about backgrounds is radioactivity. Now, radioactive backgrounds, so what I'm thinking about are like Compton scattering. So there's radioactive decays of materials that are inside in the walls in your hole, right, where you put your experiment. Radioactivity is all around us, so there's always events that get created. And they create photons, and those photons can also scatter off your skipper CCD or your silicon device and create electrons. Okay? So what you need to do is you need to shield your device well enough that you can avoid these photons, these Compton backgrounds. Okay? So a lot of work needs to go into this. But the nice thing is that the typical energy scales of the typical energy depositions of radioactive decays are of order MeV, keV to MeV. So they're very high compared to the energy scales we care about, which is a few eV, as we've seen. So they actually are not as important for sub-GeV dark matter searches as they might be now for the current generation of big WIMP experiments. So you're sort of sitting on the low energy tail of the radioactive backgrounds. Now, of course, they're still crucial, but the typical energy scales are higher. So let me just say typical energy scales of order keV to MeV, not order eV, okay, or lower. But for example, includes Compton scattering of a photon that comes from some radioactive decay of an electron in your device, which creates electron recoil background, gives fake dark matter signal. So one nice thing is that in general, these backgrounds from the Compton scattering are flat. at the lowest energy scales that we care about. So if we go back to our little spectrum that we have of dark matter. So if we look at the energy position for an electron and the rate, so dr, de, the dark matter signal, right, does something like this, falls very sharply, but the backgrounds are pretty flat. So this is your dark matter, and this is your Compton background. And of course, if you go to higher energy, so this is, I'm talking about like maybe, let's just take the scale that I had before, like 40 eV. Okay. So on these scales, it's pretty flat. And the hope is that, and as you go to high energies, there'll be some structure from some gamma ray line or something, right? But the lowest energy, you're sort of just sitting on some tail, which is pretty flat. And the hope is that as long as you shield your material well enough and you handle it well enough and you make it pure enough, this background is going to be quite low. And again, you see that as you lower your threshold, you should just see this huge dark matter signal, coming out above some background. And for Sensei, for example, the 100-gram-year experiment, the goal is to have some pretty simple shielding in order to avoid this Compton background, that you basically get 0 Compton background events in your dark matter signal at a few eV. Okay. But now, if you make it a kilogram experiment like DAMIC-M, you need to work harder in terms of making it clean. Okay. And if you want to make it 10 kilogram, you have to work even harder, and that's where the challenge is. That for Sensei, you really need to be very careful to make sure this background is low enough that it doesn't interfere with the dark matter signal, and that just becomes progressively harder the more exposure you have. Does that answer your question that you had? Maybe. I think it was you, right? So basically, it just gets harder because this background, you need to work pretty hard to have a background-free 100-gram-year exposure in silicon towards Compton background, and you need to work 10 times harder for a kilogram year and 100 times harder for a 10 kilogram year. Okay. There's some other backgrounds which are,
how does the background scale with the size of the detector? Can we think about that as a roughly linear?
Yeah, just scales with exposure. Yeah, like this background scales with exposure, yeah. Right, because you've got more
like a mass year.
Mass times time, yeah. Okay. Good. So so this is an important background for the MeV, for the searches for electron scattering down to MeV. There's actually another important background which will be important for searches for dark matter nuclear recoils at very low energies. So that's actually an important one for lower masses. So let me just say this. So this is important for MeV dark matter electron searches. For sub-MeV dark matter searches for nuclear interactions. There's a very interesting background which comes from coherent photon scattering. So as I just mentioned, there's lots of radioactive backgrounds from photons. And if you imagine you've got some photon that has an MeV of energy from some radioactive decay, what can happen is that can enter your crystal and scatter of multiple atoms and coherently scatter. And that creates a tiny, tiny energy deposition of phonons. Okay, it'll create some tiny little nuclear recoil signal. And that turns out to be very important for the low masses, at low recoil energies. So you have a spectrum where this is the sort of the nuclear recoil energy, and this is the rate. And schematically what happens is that this background looks something like this, where the transition is about 1 to 10 eV. So if you want to do nuclear recoil searches, look for tiny depositions from dark matter scattering of nuclei with some type of interaction. You have to worry about this background, so it's pretty small above 10 eV, but if you look for tiny, tiny energy depositions to probe sub-MeV dark matter down to kV masses, for example, this background becomes large. And what you need to be able to do is you need to be able to detect when an MEV photon entered your device so that you can veto those events, because you're going to get some tiny nuclear recall signal. So you can do that. So you can deal with this background by vetoing photons. So whenever you see an event, so you have some other device, some other detector outside your dark matter detector, which senses photons, MEV photons. That create this fake dark matter nuclear signal. So you need to be able to veto photons pretty effectively, and that people think we should be able to do, okay, up to a factor of 100 or so. But that also needs something that needs to be demonstrated. But that's one background that was already identified. Questions on those? Yeah.
What makes the simple way to think about the background shape looks so different between these two? For the low energy, the background is much larger here, but you struck this back for you.
So this background, so it's coherent, which means that the lower the energy deposition, the lower the momentum. And the lower the momentum, the more of the larger the number of atoms you see. So it's more coherent over a larger number of atoms. So it just increases a lot. So that's why it rises at low energies. Okay. Okay, good. And then neutrinos, solar neutrinos, I mentioned this yesterday a little bit. They are not important, turns out, for sort of, let me say it differently, they only become important background for exposures. Just happens to be, that's how the numbers work out, for exposures larger than about a kilogram a year. Okay, so for Sensei, we don't expect to see any backgrounds for solar neutrinos. For DAMIC M, one might expect to see maybe one event or something. And for Oscura, if it's 10 kilogram, you might expect to see several nuclear neutrino events. But those will be sitting at the very lowest energy band. So they're not that important compared to like dealing with the quantum backgrounds or so. Okay. And then if you look for phonon signals, then you worry about vibrations. You worry about electromagnetic interference, right? The tinier the signal you look for, the more challenging it will become. And then the big thing, the big worrying background is unknown, right? And I think it's foolish to think that we figured out all the possible backgrounds that might exist at low energies. We will learn things as we push down to lowest energy scales. And who knows if we run into some problem or some unsurmountable challenge or not. But that's the big thing. And the big question for people in the field, if you're an experimentalist and you work in this field, the big question is, when do you believe that you've discovered dark matter? Okay. And when do you think your colleagues that are not on your experiment believe that you've discovered dark matter, which should be the same threshold, but maybe it's not always. Okay.
Convince others.
Convince others. Yeah, that's the biggest. That's the thing. Okay.
You could detect dark matter with all these different experiments from the source that you can.
Right. So I think personally, I think it's going to be very hard for one single experiment to be convincing of anything. You want different groups of people doing something with different devices, right, and see the same thing.
Right.
So eventually, I think people will believe it. But I'm just saying, it's hard, right?
Yeah.
Because you just don't know always what you're dealing with. And it gets progressively harder the lower in mass you go. Okay.
Once you discover it with one experiment, you can know what you're looking for.
Yeah, absolutely. Yeah, no, I think it's a solvable problem. But I'm just saying, if you want to put out a paper claiming the discovery of dark matter without having someone else having verified it, right? Of course, there's a desire to be first. But also, people have done this in the past, and it's become foolish, right? What did you say?
Also a desire to be right.
And also desire to be right, yeah. And sometimes they conflict. well, yeah. Anyway, so we've had examples, of course, in the history of science where people have claimed amazing things and they've turned out to be wrong. Right? All right, good. So yeah. So let me just write here. When will you believe a discovery? Okay. I can say that the first time people have thought about these ideas, the first time we thought about these ideas as well, the reaction from some people was that you guys have never heard about backgrounds. Right? So people can be very skeptical. And up to today, even, this is true. Right? We have not had a single sub-GeV dark matter experiment that has not been plagued by some background. So that needs to be demonstrated. Right? All right. So let me now talk about some of the other things. So, by the way, if Tim wants to erase this, don't let him. Okay. Otherwise, I have to write this again. Okay. So we've done this, and now I'm going to quickly go through these things and also go to this. Okay, and that's the rest of the lectures. But a lot of, I think, the basic setup in the current state has been set up. Okay, scintillators. So I want to give you just salient features. Okay. So you can think of this as a semiconductor, basically, but instead of looking for electron hole pairs at the end, you look for photons. So there is. So you want a low band gap scintillator. The reason, of course, low band gap is because that allows you to go lower threshold. It avoids, if the band gap is 5 or 10 eV, you're sitting above the typical energy deposition that you get for dark matter electron scattering, as we've learned. Right? You want to be below that alpha ME times 10 to minus 3 scale. So you want to be able to sensitive to the dominant thing. So you want a low band gap scintillator. So one example of this is gallium arsenide. There's others. This has a band gap of about 1.5 eV. There's R&D going on that. Sodium iodine or cesium iodine have a gap. They're insulators. So they're about 5 eV or so. So they're less ideal, but people have worked a lot with these materials, so there's potential to use them. And then, right, you don't want to use a PMT, photomultiplier tube, which is noisy, to look for these photons that come from the signal, from the dark matter electron scattering signal. But you want to use like a TES device, or you want to use maybe an SNSPD array to look for these photons, something that's very sensitive and low noise devices. Okay, but like gallium arsenide, for example, if we take the diagram, the energy band diagram, energy is a function of momentum, right? So again, you've got some structure, and this gap is about 1.5 eV, as I said. Turns out gallium arsenide is actually a direct gap material, so the easiest to access the gap is directly go above, which we've seen is not what dark matter wants to do. So usually, typically for dark matter, you don't actually get quite, you have to do this sort of diagonal transition in an energy momentum space. So you don't quite have the 1.5 eV gap, but it's close to that. But the idea then is as you push the electron up, you get photons out as the electron decays back down. Okay, so the electron will recombine with the hole, and you get a photon. So get gamma from, for example, electron hole recombination, or you can dope these materials. So in particular for gallium arsenide, actually you want to dope it with silicon and boron, it turns out, and then you can get photons out. Use doping. In this case, with silicon and boron. Okay. Anyways, you look for photons. So use TSs, SNSPDs, or MKIDs to look for photon. And the photon is 1.5 eV of energy, and I was mentioning that there's a TES. We expect over the next year to have a TES that's sort of pretty large scale that can sense an EV photon. So you can actually do this type of experiment. And the nice thing about scintillators, I think, right, is so it competes, of course, directly with the semiconductors, which one at the end of the day is better. I think that's not completely clear. I think there's some hope potentially that you can use a scintillator and scale it up easier. Okay, so gallium arsenide is a nice material. You can make it pretty pure, the material, and maybe you can scale this up larger. You don't need to apply an electric field, for example, across the device to get an electron out. The photon will just be created and then just come out, hopefully. So you might be able to make it larger. Okay, so they might have some advantages over semiconductors. But certainly in terms of the development, it's behind the semiconductor developments. All right, so then very cool other materials. So graphene, so two-dimensional targets like graphene have been discussed. So this is an idea from 2016 by Yonit and company. So these are two-dimensional targets. So you can imagine like a two-dimensional sheet of carbon arranged in a proper way to give you graphene. So it's the problem, of course, is two-dimensional. So to get a lot of mass is hard. You need to have lots and lots and lots and lots of sheets to get a decent amount of mass. That's the challenge. But it has some cool things because here, so the idea was to eject an electron from this graphene sheet. So that takes about an energy of about 5 eV, sorry. And so the graphene sheet is about 1 atom thick. And the nice thing is that this idea can potentially give you directional information. So I mentioned all these backgrounds, right? And one way to overcome the possible backgrounds is if we have some directional information, because we believe that the dark matter, the wind, right, is coming from the constellation of Cygnus. So you have a preferred direction for where the dark matter is coming, interacting with the detector on Earth. So if you have some way of confirming that most of the signal actually comes from a direction, that's a pretty, nicely convincing, maybe not completely convincing, but it's sort of a very nice piece of evidence for dark matter. And so you can imagine some sheets of graphene and you apply some electric field where you have these sheets of graphene so these are the sheets, and the dark matter will come in, scatter off your electron here, and the electron gets ejected, and you can actually measure the angle of ejection. So there's electric fields across this, and the electron will travel in a certain direction, and depending on what angle it travels, you can see where exactly it came from and where it hits and so on. So you can potentially see what direction the dark matter came from by measuring the direction of the electron. So this gives you directional information, and that's of course a great discriminant. Yeah, that depends on the electric field. So I think here the electric field is like this. So it gets some kick of energy from, who asked me this question? Sorry. Oh, thank you. Yeah, so it gets a kick from the dark matter, right? And then the electric field will pull it back down. And then it hits somewhere here, and you measure the signal there. So you sort of get, you know where it's coming from, and you know what the electric field is, and you can figure out the momentum, etc. Okay. So this gives, this is potentially a great discriminant. Right? So the challenge, though, is, of course, to get a lot of mass. Is to get large mass. But I think, for example, if these first-generation experiments, like maybe with Super CDMS using the TESs or Sensei or DAMIC-M, sees a signal, this will be a great way to try and verify a potential dark matter signal where you get the directionality. But it's challenging to get of order 100 grams, because I think order 100 grams requires a sheet that is of order 1 billion centimeters squared of area, which is the size of this room, or a bit bigger. Okay, well, some cube, some fraction of this. in terms of having sheets, enough sheets to create the electric field, etc. That's right,
10
right?
meter cube.
10 meter cube, yeah.
Or you just tile the entire old city into this one.
Yeah. Good. Okay, and that's the goal. There's an attempt, of course, by Ptolemy G3, I think it's called, right, to do this. Okay, but it's a very challenging experiment. But I don't think this is going to be the first experiment to discover dark matter, but this could be a great way to confirm a signal if you see it. If you don't see a signal, right, you're probably not going to see anything here either, because silicon detector will probe the relevant parameter space before. Okay. All right, very good. So let me just say, great way.
We're gonna go for 5 more minutes.
Okay. You're already warning me not to go more than 5. Yes. That's fine, yeah. Okay. I will stop. Okay. Let me just briefly mention 2 other things, and then I'll stop. So there's diamond was thought about as a target. Right, that was one of my things that I wrote down. Diamond, there we go. We're moving down the list. So I won't have too much to say about this. So diamond has about a gap. If you want to use it as an electron, the dark matter electron scattering experiment has a gap of about 5 eV. So it's above the silicon band gap, right? So you can't quite get the same low mass threshold. But for nuclear recoils, the mass of carbon, which is in diamond, is less than the mass of the silicon nucleus or germanium. So for nuclear recoils, you can access lower masses, lower energies. And of course, you can also look for dark matter nuclear interactions that create some phonons, which I'll talk about this afternoon. So, and there might be hope that this has a better background, a lower background, okay, from infrared photons. Maybe lower background. Wait, let me just say here. So this is lower nuclear recoil sensitivity, and maybe lower backgrounds. Okay, so I'm clearly not doing justice to all these ideas, because all of these are, big, great, long papers. But I want to sort of just give you some salient features. Okay, there's a lot of activity going on. Okay, great. All right, just to sort of mention all of them. Then there's something called, this was a very recent paper, aromatic organic targets. So these are molecules. Aromaticity is not smell. It's a certain property of how the atoms are arranged. Okay, in the molecule. So these are molecules. So there's some carbon, oxygen bonds, etc. So it depends how the ring is formed. That is the definition of aromaticity. But anyway, you can look for dark matter electron scattering in these devices as well. And recently, what was done, they used a scintillating molecular target, which was some scintillator, which has the name EJ301, okay, which I didn't know what that was. But things like benzene and oxidine are examples of aromatic targets as well. And they just looked for dark matter electron scattering in a 1.3 kilogram of material. They put some noisy PMT next to it. They had some data. And they just measure what came out. And they were able to put a limit on dark matter electron scattering that was basically competitive with the Sensei prototype limit or the TES prototype limit from CDMS. So that's sort of a cool thing. So recent limit from a 1.3 kilogram target. All the references, by the way, I will make available online, right? So you can also, if you're interested, you can also look at these things. So there was a recent from 1.3 kilogram target, competitive with Sensei prototype limit and CDMS. And then, of course, yeah.
Molecules, so they can also do nuclear recoils?
Yeah, so that I'll talk about this afternoon, how to use them. But I don't know if they can because the signal will be a little bit different. So here you get like order EV photons out, and you just look for them. Of course, you can also now do this much better. Instead of using a noisy PMT, you use a TS or an SNSMD or an MKID array to look for these photons. Then you can also do better. All right, good. So I'll stop here. And this afternoon, we'll very briefly finish the dark matter electron scattering. Don't have too much more to say about this. And then we'll talk about the nuclear interactions, okay?